Now let's see what is involved in making the actual calls between the client and the server. And you'll see that all the kernel copying overheads are eliminated in the actual calls. What the client stub does on the client side is when the client makes that call s.foo, the client stub is going to take the arguments and put those arguments into the A stack. Ignore this result for a minute. So the client stub is going to prepare this A stack with the arguments of the call. And in the A stack, you can only pass arguments by value, not by reference. And the reason is that this A stack I mentioned to you is mapped into the client address space, and shortly it's going to be mapped into the mapped into the server address space as well by the kernel. And since only the A stack is mapped into the address space of both the client and the server, if this has pointers pointing into other parts of the client address space, server is not going to be able to access that. So it is important that the arguments are passed by value and not by reference. And the work done by the stub in preparing this A stack is much simpler than what I told you earlier about the general RPC mechanism of creating an RPC packet, where it has to serialize the data structures that are being passed as arguments. In this case, it is simply copying the arguments from the stack of the client thread into this A stack. That's what is being done by the stub. Then the client traps into the kernel, making a procedure called s.foo that results in a trap. And at this point, the client stub is presenting to the kernel the binding object associated with s.foo. So the binding object I told you is the capability that this client is authorized to make calls on s.foo. So once the BO is validated by the kernel, it can then see what the procedure descriptor associated with this BO is. And this procedure descriptor is, as I told you, the information that is needed by the kernel in order to pass the control to the server to start executing the server procedure corresponding to this particular RPC call being made by the client. Now recall that the semantics of RPC is that the client, once it makes this RPC call, it's basically blocked. It's waiting for the call to be complete before it can start resuming its execution. Therefore, as an optimization, what the kernel could do is borrow, because all of this is happening on the same machine, the kernel can borrow the client thread and doctor that client thread to run on the server address space. Now, what do I mean by doctoring the client thread? What I mean is, basically, what you want to do is you want to make sure that the client thread starts executing in the address space of the server. And the PC that the client thread is going to start executing in is the entry point procedure that is pointed to by the procedure descriptor. So you have to fix up the PC, the address space descriptor, and the stack that is being used by the server in order to execute this entry point procedure. And for this purpose, what the kernel does is it allocates a special stack, which is called the execution stack. I'm not showing you in this picture, an execution stack or E stack, and that is the stack that the server procedure is going to use in order to do its own thing, because a server procedure may be making its own procedure calls and so on, so it is going to do all of that action on the E stack. So the A stack is only for the purposes of passing the arguments, and the E stack is what the server is going to use in order to do its own work.